Okay, so we were talking about this one, yeah, the Culling-Sutherland algorithm, and these outcodes allow us to do trivial accept and trivial rejects, and they may be these trivial accept reject cases, especially trivial rejects if there are lots of objects outside your viewing boundary, clipping window, you will be able to trivially reject them, many of those easily, with just these bitwise operations, which will be implemented very fast. So therefore Culling-Sutherland algorithm is fast for these trivial reject and trivial accept cases. For non-trivial cases, as I said, what we do is we iteratively subdivide the lines by clipping them against one boundary at a time. And the iteration follows a fixed order. We cannot do some intelligent clipping. I mean, if you see, for example, this, you would not start with the left one because the left one doesn't do anything. For example, if you just clip against the bottom one and the right one, you will immediately come back to a trivial case where both of the endpoints are inside. By the way, if they're exactly on the clipping boundary, we treat them as if they're inside. Okay, so for the out code to be 1, we want the point to be strictly outside, strictly less than xmin or strictly larger than xmax. And for those 4 points that are on the clipping boundary, their outcodes will be 0, meaning that when this line is clipped against the bottom and then against the right, both endpoints will have 0, 0, 0 outcodes. So it will be trivially accepted after it's clipped against these two boundaries. Now, if we started on the other hand, for example, if you follow this order, left, top, then right and bottom, we'll first clip it against the left one, nothing happens, and we're going to clip it against the top one, which is going to just clip this tiny portion here. Okay, so if you clip it against the top, you clip the line and only this small part is gone, and then you clip it against the right one, this part is gone. So 1, 2, 3, in all 3 different clippings, chain modification on the line. At the final stage you get these 2 endpoints both inside. But you could have, if you follow the more intelligent different ordering, you could have maybe do this and do the bottom boundary first and the right boundary next, and then with just 2 clips you'll be able to get the entire line inside. Okay, so but it follows a fixed order. There is no intelligent thing that is developed here, so it follows a fixed order, and like left, right, bottom, top is such an order. We pick an outside endpoint first. We start, by the way, we first pick a point. If it's not trivial, which means one of the points has to be, at least one of the points has to be outside. If we have an inside point, if both of them are outside, we just pick one randomly. If we have an inside point, 0, 0, 0, 0, we don't start with that. We just pick an outside point and pick an edge for which V is outside. We just, for example, by looking at its code, we see that it's the left boundary. Then intersect, we do line edge intersection, which is very trivial in this case because our lines are, the clipping boundaries are all axis parallel lines. It's not just arbitrary 2 line intersection. Finding the intersection point by plugging in this xmin into the line equation of this will be simple. We find this v prime and we recompute the outcode of this v prime. If it's still outside, we go to step 1. Unless it's a trivial accept or reject. So here are some other examples. So v prime 0 now is inside. We pick v1. Actually, there is some in these slides. There are some inconsistencies with what is written here and the algorithm implementation here. This one says the iteration follows a fixed order, left, right, bottom, top. But then after we pick a vertex, we just pick an edge for that, for which v is outside. So this shows that there is no fixed order of boundaries, basically, based on what we have picked here. We just find if it's not going to be clipped like this. For example, if we pick this edge here, we don't actually clip against the left edge if this one is chosen in that first step, okay? Because for the left boundary, it's inside. So it means it's inconsistent with what is written here, left, right, bottom, top boundary. So it's not that critical, okay? You don't need to follow this algorithm to the point. There may be different, maybe implementations of that in different places. Just know that if there are non-trivial cases, there is some iterative process going on in which we try to clip the line iteratively by each clipping plane one by one until the line is trivially accepted or trivially rejected. For example, for this case here, it's going to be trivially rejected, for example, after this after clipping it against the left one. For example, how can we trivially reject this one? Let me show you that. For the left boundary, when we clip it against the left boundary, it's going to be here, okay? The left boundary just cuts this line here, and the endpoint, as you can see, both endpoints are above. They're strictly above the top boundary, which makes this, if you bitwise and the outcode, you recompute the outcode of this clipped v prime, you see that with respect to the top boundary, its outcode is 1. The outcode of this one for the top boundary was also 1, so it immediately becomes a trivially reject case after we clip against the left boundary. So here maybe we can understand this part in order to avoid this inconsistency. We can say this fixed order or some arbitrary order is established when, for example, a vertex v0 may be outside. It may have multiple outcodes set to 1. It may be outside of multiple boundaries. Okay, by the way, can we have, let me ask you this, can we have all the outcodes set to 1 for a point? Can we have 1, 1, 1, 1 for a point? I think it's not possible, right? Oh, yeah, and there's a question that I missed. In 3D, yeah, exactly, that's a good point. In 3D, we are going to do plane intersection. Our clipping boundaries becomes planes, and we have 6 planes, which means that we can answer this question, for example, in 3D, how many regions are we going to have in 3D? I think we are going to have 2 to the 6 regions, we are going to have 6 bits, that's for sure, right? We have 6 major planes. 3 major planes, but 2 for left, right, top, bottom, front, backwards. So we are going to have 6 planes in 3D, and we will have, it means that we are going to have 6 outcodes. And how many regions do they define? I think 9, is it 27? No. Is it? I mean, if it's 6 bits, I can say that there are 2 to the 6 different cases there you can have, but it doesn't mean, as you can see here, we don't have 16 regions. Here is 9 regions. I think 9. I can see this 9 stacked, three 9s stacked on top of each other. There will be 27 regions, right? Or am I missing anything? 26? Yeah, maybe. I would 26 outside, 1 inside makes, yeah, exactly 26 outside, and one of them is that inside region, which will make 27. So yeah, 3 stacks of just in 3D. Just think about this. There will be a top and bottom plane that is on this, which will give you. So there are 9 regions here. There will be 27 regions in total. One of them is the inside region, 26 outside, and but there will be 6 bits in total. Not all of them are possible, as you can see here. We don't have, we're just looking at this. It's not possible to have more than 2 bits of a point set to 1. We cannot have 3 1 bits here, okay, at most 2. These corners, as you can see, this one, and this point, we have 2 bits set to 1. We don't have 3 bits or 4 bits set to 1. Yeah, but yeah, good question. This is how we can extend it to 3D. But yeah, if it has more than 1 bit set to 1, we pick one of them with respect to this order, maybe. So this iteration follows a fixed order. We can make use of this statement in order to be not contradictory to in step 1. So for which v is outside, it may be outside for 2 different planes. We pick one of them by following an order. All right. So, I mean, this algorithm has some intelligence built on it. As you can see, we pick a particular point which is outside. We don't pick a point already inside. Okay. Or maybe, yeah. Or also the entire algorithm here, step 1, 2, 3, 4. It's actually I probably got it wrong. It's not contradicting like this. This entire algorithm is run for the left plane first. Okay, so therefore it's going to be run 4 times. Okay, so for the left one, we pick an outside point. When I say we pick an outside point, we pick an outside point with respect to the left plane. But then no. Then step 2 is contradictory. If it's here, we run this algorithm entirely for the left plane. How there's this pick and edge doesn't make sense, because left is the edge that we're running right now. So sorry for confusing you, but it's not that complicated algorithm, as you can see. Just we follow a certain order of boundaries, clip them one by one until we get a trivial accept or reject. So this one will probably a better example. Here we first clipped off against the left boundary, then we clip against the right boundary. Again, this one is clipped against this right one, but this sequence of steps, I think this algorithm here is confusing. It's this 18th slide, because if we follow the algorithm for this one, this v0, actual v0 prime is now completely inside. We shouldn't pick that one, but I think we pick v1. Yeah, it's not confusing. It's still following the algorithm. Now we pick v1, which is the outside, and we clip it. It's outside with respect to v1 is outside with respect to the right and top boundaries. We pick one of those top and right. We could have clipped it against the top boundary, but right boundary comes first, so we clip it against the right boundary, and we got this v1 prime. And at this point, where we have v0 prime and v1 prime, both of them are inside trivial except case, and we stop at this point. There's another example here. May need to perform needless clipping. v0, v1, they are both outside. We pick v0 and we clip it against the left, as the order suggests. We first, then left, and then the other out is the top one. But we clip it against the left, and we are left with this v0 prime. And then we again get v0. It's also still outside. And now we clip it against the top boundary. So we had to clip v0 twice, both first against the left boundary and against the top boundary. Okay, now let me try to... let me read your question. So for this small example we have this partial example. When we make the snip along the left border, one of the endpoints of the bottom parts end up on the left line. Yeah, so this one ends up on the left line. So this one is inside. That's why we continue with v1 with respect to us. And it's completely inside. Its code will be 0, 0, 0 at this point. The previous one. This one here had this example. This is the same example in that one, or maybe the one on the top left corner. Yeah. This one here was. Is it? Oh, the V1, the top left. Oh, okay, this one. Yeah, the small one, for example. I think you're. Let me get my annotation on. You're meaning this one, right? Or I can give you the annotation rights too. Okay. So for this one, so when we clip it, so it becomes on the border here. So it's actually when we clip it, when this top left one, when we clip it against the left plane, uh, it becomes inside the left border actually. So it's exactly on the left border, but according to the left border, this clip point, if this was V0 and if this is V0 prime, V0 prime's outcodes still makes it inside with respect to the, after it's clipped with respect to the left border. So its left border, which was its rightmost bit, it's going to be 0 at this point. So if you look at its outcodes, it's going to be 0. If this top border, I think it was the, I think it's going to be like 1 0 0 0 0. Let me write it again. This is the top boundary. So as you can see, it's inside with respect to the left one, with respect to the right one, with respect to the bottom one. It's only outside. The one that is on the border here, it's outside only against with respect to the top one. So when we look at it, it becomes a trivial reject case, not because it's outside of the left one, but because of this top one. According to this top boundary, it's completely outside. And if we had, I mean, you may ask that if, for example, if this line was passing just on this one, we would actually have it. I think when we clip it in the last part, I mean, if it was passing the corner, that corner it will be clipped finally to that single point that is the corner point, which will be trivially accepted in the last stage. So if it's just passing, if it's just a point on some corner, it will be accepted trivially after it's clipped against everything. So yeah, so this one, as you can see, according to the, we check for this one, we counted inside, but against the top boundary, as we decided like this, its outcode for the top one, for this, if this is V1, for example, its outcode is also 1. So when we bitwise AND it, we get a non-zero bitwise AND, whatever the others are, for example. It will get a non-zero AND for them, and it will be a trivial reject case this time. So does this answer your question? How about the partial line? This V0, V0 prime. Oh, okay. For example, if it is something like this, if you look at this V0, V0 prime, it's not trivial accept or reject because V0 prime here is, as you can see, it's not completely outside. So it's this example. If we had a line that is like this, that is partially on the left border, so this is V0, V0 prime. If you look at the outcodes of this one, this is not a trivial reject case because V1 is inside the left border. Okay, so this is not a trivial reject case. So what we will do is we will probably clip it against, for example, if you clip against the top boundary, you may end up here. I mean, what will happen is after clipping, at some point you're going to get this one, which is, I mean, if we have a line, if we start with a line like this, if you clip it against the top, for example, I mean, one thing you can do is, if you start with V0, it may be clipped and V0 prime may be exactly on this V0 prime here. So it may end up being a single point after clipping this V0 against this one. And both of them are going to be inside the left one. Okay, but it doesn't cause a problem for us because according to the top one, when we come to the according to the top one, at this point it's going to be a trivial reject. We can get trivial, this line will be trivially rejected at some point, either as a point like this, or if we first clip, for example, V0 prime against the top one, it will be V0 and this V0 double prime, they will be both, so this was the left boundary here, they will be both strictly left of this line, so they will be trivially rejected. So these things being at the boundary considered inside does not cause any problem for us. As I said, the most extreme case where we have a line passing through a corner of this clipping window, what will happen to this one? Should this be trivially rejected? No, what happens is that this point that is at the corner will be the final clip thing that remains and which will be trivially accepted at that point. That single point, which will be a degenerate line with, I mean, at some point you may have V0 and V1 both becoming the same point, exactly the same point, and in that case it will be trivially accepted, again, this as a single point. Okay, so the boundary is considered as inside. So I hope this answers your question. I will continue if it's clear now. All right. So yeah, we may need to perform some needless clipping. We may end up with degenerate cases like having a single point like this. But yeah, the boundary itself is as if the boundary is considered inside. So when we clip against this point, this end point is actually inside of the left boundary. We see that it's outside because when we compare it against the top boundary, it's strictly above the left above the top boundary. So this line, for example, we need to clip it twice until we get to this part, where after that point it's going to be trivially rejected. But we first clip it against this one, maybe clip it against the right one, and when we clip it against the right one, we are going to end up with this line, which is the partial. So this second right-hand side will be clipped out. So we are going to be left with this middle one. But when we clip it against this, so when we clip it against the top, we start with this order, this will remain. Whatever is remaining at last, it's going to be completely rejected. Whether this V1, V0 double prime, it's completely under right, so that trivially reject at this next step. We could have trivial rejection, for example, if we perform the clipping against the right boundary with respect to V1, we could have this part could be left out as the blue left out part. So this part may be blue left out, but again, the remaining part here is a trivial reject case with respect to the top boundary. So after every clipping step, we perform this bitwise AND operation to see whether it can be trivially accepted or rejected. So these bitwise AND this trivial accept or reject case is checked after every clipping operation. So this is another example. We cannot trivially accept or reject this one. We pick an outside vertex A, pick an edge that is outside. We pick the left one, so it is clipped. It becomes C. Now we have C and B. Again, we pick an outside edge. Let's see. Now C is our new endpoint. Its outcode will be 0, 1, 0, 0. As you can see, with respect to the left boundary, which was this one, it's now inside. So C is inside with respect to the left boundary at this point. The only edge we can select for C is now this boundary, which is the bottom boundary. Okay, so bottom is the boundary where C is outside. So we clip against the bottom. Now we get this point D, and then D is completely inside at this point. It's 0, 0, 0. Now we can still not trivially accept or reject. We should proceed with point B. We select B with as two outcodes. We again pick one of the edges in which that is outside, which is the right edge. We pick against at this point, it's going to be trivially accepted. If we have picked this one to clip B against, then again we have to do two clippings. This will be E, then this will be F, until we can trivially accept this. DE line is now a completely line segment which can be trivially accepted. Okay, so and the line for line intersections, we can use the parametric line equation of our V0, V1 endpoints of our line segments easily. So this is our parametric line equations. And when we are doing the intersection, all we need to do is we plug in, we find this t by plugging in. So we just, for this xt, we can plug in, for example, xmin. If we are plugging against, if we are intersecting our line with the left boundary, we just set, for example, for the left boundary, the intersection occurs at x is equal to xmin. So we just set this to xmin. There's only one unknown, which is t. After finding this t, we plug in that t here, which we find the y coordinate of the intersection, and this is how we can find the intersecting point. So one of the coordinates of each intersection point will coincide with one of the boundaries. Okay, when you're clipping against xmin, xmax, your x coordinate of the intersection point will be xmin or xmax. And when you're clipping against the bottom or top boundaries, your y coordinate of the intersection point will either be ymin or ymax, depending on which boundary you're clipping against. But intersection with these axis parallel lines are really easy. The same thing with plane intersection. It will not be very difficult. I mean, if we have 3 dimensions, when we are doing in 3 dimensions, we are going to be doing plane intersection, but the plane equation is really simple. X is equal to x max is our plane for the right clipping plane. And we just plug in x max to our line equation, parametric line equation. We find the t value for that line equation. Parametric lines in 3D, they're still like one-dimensional. X is equal to x0 plus some x1 minus x0 t. So this is here in the previous equation, this was d that we had, the direction of our line. So basically, if you plug in that, d times tx max is equal to this x0. So x max is equal to x0 plus Tmax times x1 minus x0. It's the same equation. After you find this Tx max, you just plug in this Tx max in this y and z equations to find your intersection point. As you can see, the x coordinate of your intersection point is exactly x max, and the other is just when you plug this in, you're going to find the intersection point easily with parametric line equations. Yeah, so the summary of Cohen-Sutherland algorithm, it has a lot of advantages. So trivial except trivial reject cases, if they're high in your scene, it's a very fast algorithm. But it has some disadvantages. These non-trivial lines can take too long to clip. You do it iteratively, a number of steps. And testing or clipping undone in a fixed order, the algorithm sometimes perform needless clipping, making it a little bit slower in these cases. Now we're going to jump to an alternative algorithm to Cohen-Sutherland for the same problem. For still line, we are still at the line segment clipping, line clipping. This Liam-Parsky algorithm, it doesn't have these outcodes assigned to these values, but for each boundary, the line is labeled as potentially entering the clipping window or potentially exiting the clipping window by just looking at the x coordinates of this v0, v1. So if we have a line from v0 to v1, as you can see, and if you're going from, I mean, there's some beginning point and end point. I mean, from v0 to v1, let me tell you why we call it potentially. Look at this. So this one, this is v0, this is v1, and again this is v0, v1. So when we are going from v0 to v1 here, because we are going to have direction to our lines, because we are going to, in Liam-Parsky algorithm, we are going to model our lines as parametric line equations, which will have some starting point v0 and some direction. Okay, so this is our line equation, v0 plus v1 minus v0t. So we are going to have some direction from v0 to v1. And it could be like this. v0 could be here, v1 could be here, okay? Now, if if V0 is here, V1 is here, with respect to the left boundary, actually with respect to every boundary, we are going to determine this line equation as whether it's potentially entering or exiting the clipping boundary. So if, for example, I mean, these are really simple rules. For example, if V0x is less than V1x, this one is potentially entering the left. So it's potentially entering with respect to the left boundary, right? With respect to the right boundary, if this case occurs, is potentially exiting the clipping window. So each line is labeled like this by just looking at its x, y coordinates actually, and looking with respect to a certain, this potentially entering is with respect to a certain clipping boundary. So after that, for example, how do we use this potentially entering leaving? Again, we are going to be using some trivial reject accept or trivial reject cases by looking at these. So each point with respect, so here, so yeah, and it has approximately 40% speed up over the Cohen-Sutherland algorithm. So this potentially entering leaving cases, let's see, and we say, as I said, we say potentially because it may actually, the clipping boundaries actually have limits. The left clipping boundary is from this bottom to this top, so it's not going to be entering the window if it's going above it. It's actually entering the area of the left clipping boundary, but it's not actually entering the window. So therefore it's called potentially entering, potentially leaving. It's indicated by not PL but PV. When we label them, we are going to use this acronym PV for potentially leaving lines, and these are potentially entering lines. So by just looking at the V0, V1 here, by looking at the x coordinate, V0x is less than V1x, so it's potentially entering the left edge. And V2, V3, as you can see, V2 x coordinate is larger than V3's x coordinate, so it's therefore potentially, it's not less than, so it's potentially leaving the left edge. And the situation is going to be reversed for the right edge by looking at the x coordinates. If your x coordinate of your starting point is smaller than the other one, in this case, now you're potentially exiting or potentially leaving the window. Now, this is similar for bottom and top edges. Now, here are some observations with these potentially leaving. If a line is first leaving, I mean, for each of these boundaries, we are going to find intersection points and label them by just looking at their, I mean, for each of these boundaries, we are going to label, according to that boundary, we are going to label those intersection points. If you're first potentially leaving someplace, for example, you're leaving, potentially leaving here, you could be potentially leaving at this point as well. So let me tell you. Yeah. So let me choose annotation. So you're also here potentially leaving the top boundary, but as you can see, you're not potentially entering the left boundary. You're already inside at this point. According to the left boundary, you are actually still, I mean, both of them are inside the boundary. So in order to be potentially leaving, I guess one of the lines has to be smaller than this. But here, this is potentially entering the left boundary, but it's leaving the top boundary. So if any place on the line, as you're moving along the line from V0 to V1, if you have a label PL first, then PE next, the line is completely invisible. It cannot be, part of it cannot be visible if you cannot be leaving and then entering. For example, here we are first entering and then leaving. okay, PE and PL. So we don't have PL and PE here. So therefore, if you have a case where you're first potentially leaving then entering, the line is completely outside and can be trivially rejected. So that's one thing we can use these labels. Visible lines, as I said, are first entering then leaving the clipping window. And also note that for a 2D clipping rectangle, on a line we will have 4 such labels, or for all the clipping windows. We will have, for example, for a line, it will enter and leave twice. Since we can have at most 2 outcodes 1. If you remember, we have at most, it can be outside at most twice. So for every line, any line will enter and leave this clipping boundaries once. So there will be a total of 4 like this, and 2 of them will be entering, 2 of them will be leaving. And what we are going to see that if the first leave happens before the last entrance, the line cannot be visible. So that will be our rule. If here we enter the bottom boundary, we leave the top boundary, we enter the left boundary, we leave at the right boundary. So if the first leave happens before the last entrance, the line cannot be visible. So these are again some simple trivial reject accept rules. Therefore, the if condition, I'm going to show you some pseudocode on this, some actually C code or some code that shows how this is actually implemented, the entire Liam-Barsky algorithm, but it's just a bunch of if-else statements, nothing more. So these are these t parameters, as you can see, it's saying that the leaving occurs before some entering event. So these are the t parameters, it occurs before. If the t value of a potentially leaving event is the parameter t is less than the potentially leaving, we can trivially reject this. So at intersection point, we need to also, in addition to these labels, PE, PL, we also, for each boundary, we compute the t value. We actually compute the intersection of our line width against all the clipping boundaries here. We compute t value at every edge. For the left edge, this is the t value. For the right edge, this is the. So these are all intersection of our line with respect to all of the boundaries here. And if any of them are not between 0 and 1, we can, I think, we can ignore those parts. But we don't need to do that actually. We can directly, we can look at these t values during clipping, but at this time, to trivially reject or accept these cases, just looking at the t, we don't, does not help us. In order to do the potential entering leaving labels, what we do is we look at x1 minus x0. We just compare x0, x1. Instead of comparing x1 and x0 and saying that if x1 is larger than x0 or vice versa, we just compute these dx values, the difference between the second endpoint and the first endpoint in x coordinate and in y coordinate. So these are the delta x values, and delta y values are computing by just subtracting these two values. And if and these potentially entering the left edge is just done by just looking at the sign of this dx. If dx is a positive number, it's potentially entering the left edge, and it's potentially entering the right edge if dx is a negative number. Okay, so this is how the labeling is done actually. And when we find the intersection type by just looking at, as you can see, by just looking at dx values, we have labels with respect to left, right, bottom, and top edge. And for left edge, we find our t value like this, and this is what dx was, x1 minus x0. Again, these are our intersection points, and the algorithm will be like this. For also for lines that are parallel to edges, we can have, we do it like this. If dx is equal to 0, it means that it's a vertical line, okay, if dx is 0. Look at these two cases. It's vertical, dx is 0. What we do is we look at whether it lies to the left of the clipping window or to the right of the clipping window. These two cases can occur, left, right. If it's completely left, right, we reject it. Again, if it's completely above or below, we reject it. It may be inside like this partially, then it's going to be, we are going to clip it in the final stages. But this is for trivial rejection cases. So putting the entire algorithm together, we just, so t beginning, so the line starts at 0, and so at 0 we just label it as the beginning of the line, and this is the end of the line as t1, and we initially set visible to false. And this visible algorithm, as you can see, is just looking at the difference, whether it's the d value, the difference between these two values, if it's a negative and positive number, and we compute the intersection points t if it's greater than TL value, or if it's greater than this TE, we update this T and TL actually is updated incrementally, and as we do the clipping. For example, if we find a T value which is greater than the current TE, so we find the intersection which is larger than TE, we set it to this value. So it's, in other words, we are going to incrementally update the beginning and end of the line as we chop it with respect to left, right, bottom, and top boundaries. So it also follows a fixed order, as you can see. We first look at the left boundary, and we send the numerator x min minus x0, and this is the denominator. So numerator divided by denominator gives me the t. The denominator is also our dx, the difference of the x coordinates, and we look at its sign, and based on its, if its sign is positive, then it means it's potentially entering. We find the intersection point. If the intersection point happens to be larger than the current endpoint of the line, then the line is completely not visible, which means that the line is completely clipped by this clipping plane. So this is a complete clipping case. But if the t value is greater than e, we clip it from the beginning point and update this one. Similarly, this is the same thing for the right hand when it's potentially leaving. For potentially leaving lines, update the endpoint, not the starting point, but they update the endpoint of the line if it's possible. But this potentially leaving occurs before the beginning of the current beginning of the line, then the line is completely invisible, it's completely rejected. So the algorithm is the entire algorithm is like this. So if the denominator is 0, it means if it's a parallel to edge, we just treat it with respect to, so it's not going to be visible, but here we set it visible, and this one is done how we treat parallel edges, how we do that. Okay, so in 3D, its 3D extension is also very trivial. Another good thing about Liam-Barsky is that since it's entirely on parametric line equations, we can just add the z component easily because it's just another equation in parametric line equations. And here is an example of a Liam-Barsky algorithm, V0, V1. So we start TE and TL starts here. And the first thing is we start with, so on the left edge, with the left edge, we find this intersection point, and since it's potentially entering at this point, and the t value now is updated, t value becomes this new intersection point. And Then we come to the right edge. Edge is potentially leaving the right edge. Therefore, we update the TL here. Okay, TL is updated here at this point, and it becomes this line. So this becomes the new point, and at this point, so if we do it for the bottom edge, for example, if we start with this one, we start with the bottom edge. It's not updated. T is smaller. Again, it's potentially entering the bottom. Okay, but it's not updated because it's a small number, and it's not, again, T is not updated in this case if it's larger than the current TL. So if the intersection point occurs beyond the boundaries in certain cases when it's potentially leaving, for example, we do not update it. So the largest T and the smallest TL will give us the line that is clipped at the end. All right. So in short, so I'm not going to start the polygon clipping algorithm because we are out of time. So we're going to continue here from here on Thursday. But in short, Liam-Barsky algorithm uses parametric line equations, and it computes the intersection point. So you may argue, for example, well, how can it be more efficient than Cohen-Sutherland? Because for every clipping boundary, we are actually computing, we are doing a division and computing this t value, and we are finding an intersection here. But it's just keeping track of the single parameter p. It doesn't keep track of the xy coordinates of the endpoints of the line. So it doesn't actually compute this v0 prime, v1 prime. The points are not computed, but just where the parameter along the line is what is kept tracked. This is what we keep track of. And based on what the parameter value and whether we are potentially entering that boundary or not, sometimes we can completely, so in certain cases, we can do complete rejection of the line by just, in one of these boundaries, we can figure out that the line is entirely invisible. So complete rejection cases can occur in some of these visible functions. So when it becomes false, it's going to be completely rejected. Okay, so these are the two line clipping algorithms that we have seen. In the assignment, I'm not sure, in the second assignment, I haven't read the entire assignment yet, but whether how you're going to perform clipping. Maybe you may not even deal with clipping in the second assignment, I'm not sure, but if you are going to deal with clipping, you will be implementing one of these algorithms, and it will be stated specifically in the assignment. All right, so as I said, we are going to continue with polygon clipping on Thursday, and my plan is to finish the remaining set of slides. So we will finish clipping and culling this week, and we will start rasterization on Tuesday next week. Let me stop recording now.